The shadow mask tube. Slide number 1, please. The object of this lecture is to explain the principle of operation of the shadow mask tube, so as to help you make those adjustments which are necessary to ensure its correct operation. Before we can start, however, it is desirable that we should have some knowledge of basic additive color mixing principles. Change to slide number 2. The first thing to realize about color is that the charts of this sort, which we have all seen, relating colors to particular frequencies in the visible portion of the electromagnetic spectrum, is a chart of colors in their most vivid form, or, as we say, most saturated form. In nature, color is seldom like this, the colors with which we are more familiar being the pastel shades, the pinks, light greens, etc. Change to slide number 3. The majority of colors could, therefore, be described as relatively desaturated. The radiation, in this case, is not confined to any one frequency, but probably includes some contribution from all parts of the visible spectrum, and the apparent color now seen depends upon the frequency region of the largest contribution which is arriving at the eye. If radiations of substantially equal amount are arriving from the whole visible spectrum, we would describe the resultant light as white or colorless. However, the eye is easily fooled into thinking that a whole range of different energy distributions are being presented to it as colors apparently change, when in fact all the eye is seeing is one or more of 3 well-chosen colored lights which have been so arranged as to illuminate the same area. Change to slide number 4. To allow these lights to synthesize the maximum range of colors, one would arrange for the 3 primaries, as we call them, to be 1 red, 1 green, and 1 blue, and the object being illuminated white. Clearly, any one of these 3 colored lights, when switched on its own, would produce an area of illumination which is the same color as that of the primary which has been used. What is less obvious is the result of switching the primaries on in pairs, red with green, green with blue, or blue with red, or indeed all 3 lights at once. These last 4 conditions will produce results which are important and a little surprising. Taking the last mentioned condition first, the situation where all 3 lights are switched on at once. If the relative brightness of the lights can be varied, a situation could be found where the resulting color could be described as white. Under these conditions, it could also be found that the brightness contribution of each individual primary was by no means equal when assessed by the human eye. The lion's share, we would find, appears to have been contributed by the green light, the red light being the next major contributor to brightness, and the blue light would appear to run a poor third. It is these apparently uneven contributions of the 3 primaries which are prevailing when I refer to the lights as being equally excited. The absolute value which each assumes under these conditions, our common sense tells us, will govern the brightness of the resulting white light. Change to slide number 5. Having set the relative contributions of our 3 primaries in this manner, we could quickly establish that the subjective effect of, say, red and green primaries alone was yellow. Green and blue alone produce cyan, and red and blue alone produce magenta. So far, we know how to produce 6 colors: red, green, blue, yellow, cyan, and magenta, also white, simply by switching on the appropriate lights. Colors produced in this way will have a maximum saturation and color range which is governed by the actual primaries chosen. In that we can produce whiting all lights on at once, it is not difficult to see that we could produce desaturated colors simply by approaching that condition which we would ultimately accept as white. Several times so far I have used the word color to mean no more than a particular subjective effect, red, green, etc. As a matter of interest, the correct name for this parameter is hue, and to define correctly an object or light, we need a description which will include information about its hue and its saturation, and also a third characteristic which is much more familiar to us, its brightness. It is not necessary at this stage to go any more deeply into color theory, being now armed with enough in the way of basic facts to enable us to appreciate the reasoning behind the construction of the shadow mask tube. I have said that given 3 suitably chosen lights, we are apparently in a position to produce almost any color simply by varying their relative contributions. This is a simple process compared with a system which changed the true frequency of radiation to comply with each particular color which we wish to convey. Change to slide number 6. The face of a shadow mask tube does in fact consist of a vast number of minute red, green and blue lights, the contribution of each being variable at any instant, thereby enabling us to produce a picture element of that color which we wish to convey, and by the normal scanning process to build up the whole picture in what is apparently the original colors. You may have noticed that I have made no attempt to explain anything that has been said so far. I have merely given you a few facts, and my purpose will be to continue to supply these introductory comments which will be covering the whole range of this lecture's field, so that when we go back and discuss each point in more detail, there is a good chance of our feet remaining firmly on the ground. This is also a good time to mention that there is nothing difficult about color television. There is, however, quite a lot which is new. This, I know, is very often the same thing, especially when we get a lot of new ideas to assimilate all at once. In the opening remarks, I said that this lecture was to explain the principle of operation of the shadow mask tube. So what we must now do is, from an examination of the slides, reconcile what has been said regarding the requirements for synthesizing color with the tube's construction. Change to slide number 7. This close-up from the face of a shadow mask tube shows the 3 3/4 megacycle bars on a test card and shows some of the minute red, green and blue lights which go to make up the tube face, here under conditions where they are being equally excited. In other words, under conditions where they produce white light, whose brightness, in this case, is being made to vary at the appropriate rate. In reality, these lights are nothing more than individual spots of phosphor which have been designed to fluoresce with these colors rather than the more familiar bluey white used in the monochrome tube. Change to slide number 8. The construction of the shadow mask tube is such that only red fluorescing phosphor dots are exposed to one electron beam, whilst only green phosphor dots are exposed to a second electron beam, and only blue fluorescing dots to a third. This means that there will have to be 3 electron guns in the tube neck, and the shadow mask tube takes its name from a vital component used in its construction, which is designed to render it possible for these 3 electron beams to find their way to only those phosphors for which a particular beam is intended. So what one is doing during part of the tube setting up procedure is making sure that the stimulation which should be associated with, say, the red phosphors has no influence over the green or the blue, and similarly for the other 2. In other words, making sure that the circuits which should influence, say, the red light cannot be responsible for light from either of the other 2 primaries. As the name shadow mask suggests, phosphor masking is achieved by a shadowing process, from which you will immediately appreciate the importance of each beam arriving from precisely the correct direction. Facilities for controlling the direction of arrival of each beam are provided, and achieving the right answer for this is one of the things required of us during the process known as purifying the tube. Change to slide number 9. This slide is intended to illustrate the shadowing process more clearly and assumes the presence of only one electron beam. We see that the effective diameter of the beam is such that several holes in the shadow mask are being covered, and hence several phosphor dots on the tube face are being bombarded. This slide should also show the necessity for the electron beam to arrive from precisely the correct direction, if only the required, in this case red, phosphor dots are to be bombarded. However, let us not get too involved in the details of any one part of the subject at this stage. Another requirement for satisfactory operation of the shadow mask tube is concerned with making sure that the red, green and blue phosphors, which are being bombarded, remain those physically adjacent to each other on the cathode ray tube face. The achievement of this is known as convergence. This convergence is a twofold problem involving overall and position-dependent corrections of the tube electron beams, referred to as static and dynamic convergence, respectively. There follows now a brief introductory description of the components to be found in various positions strung along the neck of the shadow mask tube. Change to slide number 10. In order, from front to back, these are the scanning coils, the convergence assembly, the purity magnets or purity ring, and lastly the lateral blue shift mechanism. There is little need at this stage to say much about the scan coils, except to mention that they no longer have a fixed correct position nestling snugly against the glass flare of the tube, which is usual in monochrome practice. The reason for this, which will be gone into more thoroughly later on, is that it is necessary to slide the scanning coils along the tube neck until we find the position which utilizes precisely the 3 deflection centers which are necessary for accurate beam landing. In other words, the electron beams are required to be deflected at a precise position within the shadow mask tube. Immediately behind the scanning coils, we have the convergence assembly. This consists of 3 quite separate ferrite U-cores mounted at 120 degrees to each other, each core being wound with 2 separate windings for excitation from line and field-derived signals. Also associated with each ferrite core is a small permanent magnet whose influence can be varied manually. Behind the convergence coils, we come next to the purity ring or purity magnet. This consists of 2 steel rings, each magnetized across its diameter and clamped so as to be in close proximity to each other, but remaining free to be rotated one with respect to the other. This arrangement enables us to produce a transverse field which is variable from substantially zero to some maximum value, and by rotating the 2 magnets together we can vary the direction of the resultant magnetic field. Behind the purity ring is another small device consisting of pole pieces and another adjustable magnet. This is the blue beam lateral shift mechanism. I have referred in all to 6 small magnets which will be found in various positions along the tube neck. 3 associated with the convergence assembly, 2 for the purity ring, and 1 for the blue beam lateral shift mechanism. Of these 6 magnets, the 3 associated with the convergence assembly and the one in the blue beam lateral shift device, that is 4 magnets, are all concerned with static convergence. The 2 magnets which comprise the purity ring, on the other hand, play their part in conjunction with the scanning coil position along the tube neck in providing good color purity. So far, we have touched upon purity and mentioned the requirement for producing it, namely, correct direction of arrival of electron beams. What is meant by static convergence is equally straightforward. From what has been said, you will appreciate that the shadow mask tube is essentially nothing more than 3 cathode ray tubes within one envelope, each utilizing the same tube face on which to produce its raster. And static convergence is the name given to the shifting of the 3 rasters slightly by the use of the 4 magnets mentioned, so as to superimpose these 3 rasters on the tube face. Another aspect of the tube's operating requirement is known as grayscale tracking. Very briefly, this is the actual process whereby we arrange for the phosphors to be equally excited at all brightness levels. The contributions of red, green and blue light will then be relatively correct, thereby enabling the receiver to produce black and white picture elements, or indeed whole pictures when called upon to do so. We achieve this by a proportioning of the beam currents of the 3 electron guns, one with respect to the other, so as to achieve this at all brightness levels. The 3 new adjustment processes with which we are required to become familiar, which are associated with the shadow mask tube, are therefore 1. Purifying the individual rasters so as to make pure red, pure green and pure blue individual contributions to the resultant raster. 2. Convergence, which is concerned with the superimposing of the red, green and blue rasters at all parts of the tube face. And 3. Grayscale tracking, which is necessary for good black and white and indeed good color picture rendition. We shall now go back and discuss these 3 aspects, but this time in some detail. Change to slide number 11. This shows an artist's impression of a section through a shadow mask tube, showing the 3 vital regions. We have on the left the electron guns, tilted slightly so as to converge naturally at the tube face. On the right, the shadow mask, situated a short distance from the tube face. And on the extreme right, the tube face itself. These components and this layout represent the essential shadow mask tube ingredients. So let us have a look at each in turn. Starting with the guns, our interest is not in their construction, although in practice they appear a work of art, but their physical positions with respect to the tube axis and with respect to each other, namely, that none of them are on the axis. In fact, they are symmetrically situated around it, at the points of an equilateral triangle. This difference in gun position, it could be said, is responsible for the success as well as some of the complications associated with the shadow mask tube. The use of different positions is of course inevitable, because the guns would otherwise get in each other's way. But apart from this, it is necessary, because the basic principle of operation is the exposure of one type of phosphor only to bombardment by each electron beam. And if this is to be achieved by shadowing each electron beam from its unintended phosphors, then clearly the electrons must emanate from a position relative to the shadow mask holes and the phosphors which satisfies this condition. The complications which were implied as being a direct result of the guns being off-axis and in physically different positions will be considered when we are discussing convergence. Let us now move along from the guns to the second fundamental component of the tube, the shadow mask itself. This is a thin metal plate situated a short distance behind the inside surface of the glass face and following the contour of the face. The shadow mask has small holes etched through it over its whole surface area, the holes being evenly spaced and of such a size as to remove about 25% of the total area of the mask. Move on now to the third vital region of the tube, we come to the tube face itself. Change to slide number 12. No straightforward single aluminized phosphor here, such as that found in the monochrome tube, but as the present slide illustrates, a mass of discrete circles of phosphor nestling tightly together and covering the whole of the inside surface of the tube face. We must now go on to consider the tube's construction in a little more detail. The deflection centers for each of the three beams, or the fixed points from which each deflected beam must appear to emanate if it is to find its way only onto the appropriate phosphors, having passed through the shadow mask, was precisely established during the manufacturing process of the tube by photographically exposing the phosphors onto the tube face from these deflection centers and through the actual shadow mask which is to be found in the tube. If therefore the electron beam of each gun is to hit fair and square only the phosphor dots for which it was intended, quite clearly the electron beam must be made to pass through a position within the scanning coil field which is identical to this. When we bear in mind that there are three guns, each requiring its electron beam to be precisely positioned within the scanning coil field, this, in spite of manufacturing tolerances, which would result in each gun being, to a greater or lesser extent, inaccurately aimed, it will come as no surprise to find that steps have been taken to give us some control over the direction of emanation of the individual electron beams.